At 5,000 services, your kube-proxy hits 100% CPU, service updates take 30 seconds, and one of your latency numbers is measured in whole seconds. The problem is 42,000 iptables rules doing a linear walk on every connection. Cilium's eBPF data plane replaces all of it with hashmap lookups and drops production latency by 40%. kube-proxy translates service virtual IPs to pod IPs using iptables rules. Cilium does the same job with eBPF programs attached to the kernel. Both achieve service abstraction. One scales, one doesn't. Here's how kube-proxy works. Every service in your cluster gets a virtual IP. Packets hit the KUBE-SERVICES chain, which acts as the entry point, one rule per service port in the entire cluster. KUBE-SERVICES matches the destination IP in port, then jumps to the corresponding KUBE-SVC chain. That chain acts as a software load balancer, with rules for each backend pod endpoint. Finally, the KUBE-SEP chain executes DNAT, rewriting the destination IP from the virtual service IP to the actual backend pod IP. Here's the KUBE-SERVICES chain on a real cluster. Every service port in your entire cluster puts one rule here. The kernel walks this list top to bottom on every new connection until it finds a match. At 1,000 services with an average of 10 pods each, you've got roughly 10,000 iptables rules in the NAT table. Every packet walks through them sequentially until it finds a match. At scale, iptables lookup takes 50 to 200 microseconds per connection. IPVS improved that to 5 to 20 microseconds, but eBPF blows past both. The lookup cost is only half the problem. Every time a pod dies or a service changes, kube-proxy rewrites the rule set. Before Kubernetes 1.28, that meant the entire chain, thousands of rules rewritten on every endpoint update. Since Kubernetes 1.28, kube-proxy does more minimal, targeted updates, only rewriting chains that actually changed. But even with targeted updates, large-scale rule sets impose real overhead. The linear lookup cost is still there. Here's the cliff. Netflix measured the bottleneck beyond 1,000 services. AWS moved EKS to IPVS mode for clusters over 1,000 services to avoid network latency. At 5,000 services, kube-proxy is at 100% CPU. Enter Cilium. It's an eBPF-based CNI that can fully replace kube-proxy. Same service abstraction, completely different data plane. Requires kernel 5.10 or later, and Kubernetes 1.31 through 1.34. Instead of iptables chains, Cilium uses eBPF hash maps. This is a generic kernel map type with no restrictions on key or value structure. It's implemented using a hash table, allowing lookups with arbitrary keys in constant time. The lookup function returns a pointer to the map value in kernel memory, not a copy. That means 0 allocations, 0 copies, just a pointer to reference. Complexity matters. iptables is order n. Every new service makes every lookup slower. eBPF is order 1. 10,000 services cost the same as 10. Measured latency numbers. iptables takes 50 to 200 microseconds. IPVS takes 5 to 20 microseconds. eBPF latency is even lower than IPVS, 2 to 5 microseconds for the entire lookup and rewrite operation. Here's the mechanism. Cilium attaches eBPF programs to syscall hooks, specifically Connect4, Connect6, and SendMSG. When your application calls connect to a service VIP, the kernel executes the eBPF program before the TCP IP stack even synthesizes packet headers. The Connect and SendMSG BPF programs do forward translation of the socket address structure. The translation is based on the socket struct. There is no packet-based NAT. The socket is rewritten before the kernel builds packet headers. The application thinks it's connected to the service address, but the corresponding kernel socket is actually connected to the backend address. Therefore, no additional lower layer NAT is required. No per packet overhead. For same node pod-to-pod traffic, connection setup time is near 0 because the kernel never builds a packet. It just connects the two sockets. East-west load balancing rewrites service connections at socket level, avoiding overhead of per packet NAT and fully replacing kube-proxy. Socket load balancing intercepts connect and SendMSG system calls to perform load balancing at the beginning of the connection. It depends on C group version 2. Kubernetes pods still use C group v1, but Cilium mounts C group v2 and attaches BPF to the root C group. Hybrid use works well. Here's the installation. You enable kube-proxy replacement with a single Helm flag. Cilium needs your API server endpoint so it can synchronize service state directly from the Kubernetes API. After installation, verify the replacement is active. You want to see kube-proxy replacement enabled and mode set to strict. Strict mode means no fallback to kube-proxy, pure eBPF. Now, the migration window. If eBPF kube-proxy replacement is added or removed on an already running cluster, existing connections will break, since both NAT tables are not aware of each other. kube-proxy has its own NAT state and IP tables. Cilium has its own NAT state and eBPF maps. They cannot coexist on live traffic. If deployed on a newly spawned up node or cluster which does not yet serve user traffic, then connection breakage is not an issue. The safe migration path is rolling node replacement. Drain, delete, spawn with Cilium. After Cilium is running, delete the kube-proxy daemon set, delete the kube-proxy config map, and clean up the iptables rules on each node. You're done with chains. Now the real win, direct server return. In standard SNAT mode, Cilium rewrites source IPs and routes traffic through the load balancer. DSR allows the backend server to learn the original request's source IP and respond directly, resulting in reduced latency and improved throughput. DSR with IP/IP encapsulates load balancer traffic towards the backend in an IP/IP tunnel. The original client packet becomes the inner payload. Cilium adds an outer IP header whose source is the load balancing node, and destination is the selected backend pod IP. The encapsulated packet is routed to the node hosting the pod, where Cilium terminates the tunnel and de-nats. Standard SNAT means every response byte goes back through the load balancer. DSR means only the request hits the load balancer. The response bandwidth bypasses it entirely. That halves the load balancer bandwidth. Measured impact from CNCF benchmarks on a 10,000 service cluster. Network-related kernel CPU usage drops 40 to 60%. P99 latency drops 30 to 50%. Connection setup time near zero for same node traffic. For short-lived connections, common in serverless workloads, Cilium's eBPF connection tracking will outperform Calico's IP tables connection tracking by 40% or more. P99 latency drops of 30 to 40% compared to standard tunneling, moving from around 1.2 milliseconds down to 0.8 milliseconds. Here's the surprising part. eBPF-based solutions can outperform even the node-to-node baseline on modern kernels, despite performing additional work, forwarding into the network namespace of the container and policy enforcement. This is because eBPF is capable of bypassing the IP tables layer of the node, which is still traversed for the node-to-node baseline. But DSR has a catch. Direct server return with IP options requires Cilium to be deployed in native routing mode and may not function correctly in some public cloud environments where IP options might be dropped. Compared to IP/IP dispatch, IPv4 option or IPv6 extension header dispatch avoids Cilium-specific IP options that some network fabrics drop. To enable DSR, set routing mode to native, kube-proxy replacement to true, and load balancer mode to DSR. The dispatch mode determines how the tunnel is built. Opt for IP options, IP/IP for IP and IP encapsulation, or Geneve for tunneling. IP/IP is the safest for cloud environments. Quick recap, kube-proxy walks iptables, chains linearly. Order N. Cilium does hash map lookups, order 1. Cilium intercepts at the socket layer before packets exist. DSR eliminates asymmetric routing. Measured latency drops by 40% in production clusters. Cilium requires kernel 5.10 or later for eBPF and C Group v2 support. Kubernetes 1.31 through 1.34 are the tested versions. C Group v2 is required for socket load balancing, and you need a migration plan. kube-proxy and Cilium can't coexist on live traffic. Google, AWS, and major cloud providers have all adopted Cilium as their eBPF networking option. Google Kubernetes Engine announced eBPF data plane with Cilium in August 2020. EKS recommends IPVS or Cilium for clusters over 1,000 services. eBPF is eating the kernel. kube-proxy is just the appetizer.